What's up guys, and welcome to a new LS-DYNA tutorial. In this video we will do part 2 of the ALE tutorial. As I promised, we're gonna do a sloshing problem, so this video gonna be a quick one. If you haven't checked the first video, I really recommend you to go through that because that one I explained in more detail. So let's open our LS pre-post. Okay, so I go to mesh, shape measure. I want to make my tank, and then I go to sphere solid, the radius, let's say 0.1, and the density of the elements is 10, and then create. Then I want to delete half of it, delete by area, and then here like this, and then delete, and then accept. Okay, now I want to make the cylindrical part or the long part of the tank. So I go to element generation, then solid, then here the thickness or the length is 0.3, segment let's say is 15, and it's gonna be in the negative direction. Click by element and propagate. Then here you go, click again the right view. You can see the mesh almost the same size. I think I can make it better. I will put 20, yeah. Then accept. Alright, now I want to reflect this end to the other side, but before that I want to deform it a little bit, because as you can see in the tanker picture attached here, the starting and the ending part are not perfect half spheres. So I go to element tools, then transform, then I want to scale it. So the direction is X, the origin of scaling is anywhere on this line, and then the scale factor, let's say 1.1. Then click by part, and then scale down 1, 2, 3. Okay, now it looks more realistic. Then accept. Now I go to reflect. Then I want to reflect to this side. So I go click by part, and then the origin in the X direction, I know that it will be somewhere here, and that point will be minus 0.15 because I made this length 0.3 just now. So this is the value, then 0, 0, and then copy elements and then reflect, and then you can see it's perfectly matching here, and then accept. Now duplicate the merge node, show the duplicate node and merge duplicate nodes, and then accept. Now I will separate them to water and air. So here, this one, part number 1, let's say it's going to be air, and click by area, this half, make sure it's okay, accept. Then part number 2, this one gonna be our water, and then here accept, done. Okay, now I want to make the tank itself, the shell. I can make it solid of course, but in this example I want to make it shell because it will be lighter for the calculation. So I go to mesh, then element generation, and then shell, then solid face, and then I click by elements and propagate, and then 45. Okay, now I'm clicking on the outer surface of these two parts. So create and then accept. So click on F2. Now you have this green part which is shell, and it will be the tank. So here I do this one, transparency, and then I show everything. Now you can see like this. So this is the tank and this is the water. Okay, now one problem with the tank, because I created the tank from the surface of the ALE parts. So this Lagrange tank will be merged with the ALE. So if this is the case, I need to detach them. there are few ways to detach the elements. Here I will just show you the simple trick, which is just you move and copy. So first you translate, let's say in the Z direction, and this is 0.3. Click by part, and part number 3, which is the tank. Then copy elements, then you move up. So now you have two tanks. You have the water and the air down here, and you have two tanks. The lower tanks are fixed to the air and the water, so we don't want it. So we go to element editing, and then we delete by area, and delete this guy. Delete. Now we close this one, and then we translate back down to its original place. But we don't need to copy the elements anymore. By part, and then move down. Okay, now I have completed the mesh. So I go to Control S. I want to save this one before it crashes. So I go to desktop, and then I go to sloshing, then save. Okay, before I go to the next step, as you can see here, if you measure the length from here to here, you'll see it's 0.3. So in this tutorial, I'm using meters instead of millimeters. In the previous tutorial of the ALE, I used kilogram, millimeter, and milliseconds. In this tutorial, I'm using meters, kilograms, and seconds. So next we go define the material properties. So for the part here, I just change it straight away to tank or tanker, whatever. Now the air, the section gonna be solid ALE. So here, new, I put solid ALE, and the formulation is 11. Just double check. Yes, it's 11. Then accept. Material ID, new. In my previous video, I made fluid and vacuum. In this example, I will make water and air. So to model the water, you can use this 009. So you click here, and then you name it air, and then here you define the density 1.293 kilogram per meter cube, and then here you accept. Now the equation of state, new keyword, you can use linear polynomial. Then new, here you can say air equation of state. This one just C0 or C0 will be -1 e to the power of 5. This one in stress units, so it's in Pascal. And this one, the energy is 0.25 e to the 6, and V0 is 1. Okay, so set. So hourglass, we just use number 1, and then this is a small number 1e minus 6, and this one I call it ALE hourglass, then accept. Okay, done for the air. Now for the water, section ID is the same, material ID is null, but it has different properties, so I need to define a new one. So here null again, and then add, it will be number 2. Okay, good. Then I type water, and then this row is 1000 or 998.2, and that's all what I need to define here. In the previous example, I defined the viscosity coefficient here, but in this video I will not do that because I'm going to use a different equation of state. Then accept. Equation of state, new equation of state. So here I will use Gaussian. New, and then here I will say water equation of state, and then C1 is 1647, and then I have S1 is 1.921, S2 minus 0.096, and gamma naught or gamma 0 is 0.335, and that's all. Then accept. Then equation of state is the same, the hourglass is the same like for the air, and then accept. Now the tank. The section is not solid. Of course, this guy is a shell. So new keyword, and then shell. Double click here. We already have it here. New. We'll just make it 3 because the tank is part number 3. And then here I'll say tank shell. So the thickness gonna be 1 mm. Then accept. Material ID. I want to make it rigid because water is inside and water will not have that much effect on the tank. So new keyword, and then rigid, new, and then here rigid tank. Density is, let's say, make it of steel. We make it of steel, and this E is 200 giga. Horizontal ratio 0.3, and then the constraint, let's say it is constrained in X and it's constrained in Y and Z. So this one be 5, and it's not around and it's not allowed to rotate. Okay, then accept. Done. Okay, let me check again. Model, then part. Okay, what? Okay, this one I did not accept. One, I forgot to accept just now. One, this one 1, and this one also 1. Then accept. So this is 1, 1, 1. Okay, everything seems fine now. So what I want to do here for the boundary condition, I want everything to be moving at initial velocity of, let's say, 20 meters per second, but then the tank will suddenly stop. So to do that, first I want to define the initial velocity. So collapse all, initial velocity generation, and then set type, it will be part set, then new entity or new keyword, here part list, new, and then here I'll say LE parts. Part 1 is the air, part 2 is the water, and don't forget to insert here. I'm telling myself not to forget because in the last video I forgot to do this. Then accept. So now here I have in this set I have the LE parts. So the initial velocity will be 20 meters per second. It will be moving in the positive X direction like this. Okay, then accept. Done. Now I go to boundary, prescribe motion rigid. Prescribe motion rigid. Now add, and then part ID, it will be the tank moving in the X direction. Okay, I will apply a velocity curve. So I don't have any curve here, so new keyword, and then double click on this guy, and new. Here I would say velocity. So when times is equal to 0, the velocity is 20. The tank is moving at the same velocity as the fluid inside it. Insert. But when time become 1 millisecond, it will stop. Insert. And then let's say when time is 1 second is also stopping. Insert. And then accept. Here I would say tank movement. Here I'll put 1, then accept. Done. I want to check my curve again. Curve, this guy. So yeah, it starts here and then it drops here. I think 1 second is too much, too much. So I put just 0.015 and then replace. Accept. So now you can see more clearly here. Accept, then done. Okay, now we define the coupling between the Lagrange and the LE. And here is constraint Lagrange in solid. And then here new. The slave is the the slave should be the Lagrange part, which is the tank. So this one gonna be number 1 and this one gonna be tank, and the solid is the solid LE, which is this part set number 1. Here let's say LE or FSI coupling. Okay, number of quad should be 0 is fine because the mesh of the LE and the Lagrange are the same size. C type, okay, in this example I will use 3. Okay, normal direction only, and the coupling with all the multi-material. So it's coupling with the air and also coupling with the water inside, and then accept. Why here I'm using 3? Here I'm using 3 because it's like a closed system. But before, in the previous example, I used 4 because the system or the problem is like an open system where you have a ball dropping on of water, but here we have the water inside. If that's the case, it's recommended to use 3. So here accept, and then just save, Control S. And what else do I have? Click on all. I have control. Yeah. Okay, since I'm here, I just use the database. Okay, so I go to D3 plot, binary D3 plot, and here I put 1000. This 1000 states are okay because my keyword file is small, so the output file, the total output file will not be that big. And here control time step. Again, this is fluid problem, so reduce the default, accept, and then termination, it will be, let's say, only 15 milliseconds, which is very small. Accept. And then what else? Okay, let me collapse all. And then here again I go to control. I have this control ALE, this one -1, and this one is also -1, and then accept. Okay, so that's pretty much for the sloshing. We have one more important thing to do, which is here inside the ALE. Actually, 2 more things. One thing is here the ALE multi-material group. Okay, so this one will be part. So the first one will be air, accept, then add. Another one will be water, type here water, then accept. Okay, so the new thing in this video that I did not do and I did not need in the previous video is to define the moving mesh of the LE. So I display the tank, and then I want to here identify 3 nodes. Let's say here 1, 2, 3. You can see they're forming a right angle. Okay, instead of this one, I will just say this one, 1, 2, 3. I hide this one so it's clear. Now I go again to model and then keyword, and then here I have LE reference system node and reference system group. So first I take this one, system node, then new ID number 1, and then I input these 3 nodes ID here. So first this one is 22768, and then 22767, and then 22788. Okay, accept. Then I go here, reference system group, then add here this LE parts. So the mesh, the LE mesh of this one will be following something, and that something here I put it number 5, and it will be here. You can see automatic mesh motion following a local coordinate system defined by 3 user defined nodes, which we just defined just now. So click here, you have number 1. This number 1 is actually the thing that we just defined just now, and then accept. Then Control S. Okay, model check. Do we have any errors or warning? Okay, I have warning here. Shell. What does it say? Okay, thickness is less than 0.5. Okay, it's a very small thickness, but it should be fine. And this warning is not defined beyond termination time, so it's okay. I go here, keyword, and then I go to define curve, and then our termination time is 15, so I put here 20 milliseconds. Replace, accept, and done. The section here, I check again, is 1 millimeter, should be fine because it's rigid anyway. So I go to model check again, recheck, so this one disappeared already. So now I click Ctrl S, I save the keyword, and then I try to copy this. We have some problems with the shell, but not this warning. If you display the tank, you will see that the normal of the tank are pointing outward. So the normal by part is pointing outward. So we need to change that. So reverse normal by part and then done. So here again I show the normal, click by part. You can see now all the normal are going inside. Okay, so Ctrl S, and that's one way to change the normal. Another way is that you don't need to change the normal, you change the thing here. Okay, change the normal type here. I think this one. Yeah, left hand rule, this is the default. If you change the right hand rule, of course the direction of the normal will change. So you can either do like what I did, or you just change here. So now you save. Then I open the LS-DYNA manager. So I paste here, I run it. So let us just wait. Okay, so I think that's enough to check whether the thing is working or not. So I open the results and then click on F2, fluid, and then see whether the things are working or not. So you can see here, this is the sloshing effect. So I can hide everything and show the tank and the fluid. So the fluid or the water is just put it blue for nice effect. And then click on this guy to show our shell, tank, and then transparency, and then like this. I can also hide the mesh. And here you go. So you can see the LE mesh is moving and is actually following this green tank. Maybe this one's a bit slow, so I can, let's say, put it 2, the increment 2, so it'll be faster. Okay, so this is actually partial result. I have more longer result that I run before, so let us open that. So this is the result until 1 milliseconds. And let's see what will happen here. It's total chaos. So this is the water. And let us again color it blue. So here you have the sloshing effect. I want to rotate it and make it this side. Okay. So in this example, I did not apply any gravity effects. The gravity effects will have some influence of the result, especially when you have the running time until like 1 milliseconds. So here we have the sloshing. Okay, I don't have any results to compare with, but I can compare only visually. So I can just go somewhere here, and you can see here on the top we have something like this. And here if I compare to this paper, you can see that in the experimental results also we have some of the same effects, maybe somewhere here. And again, these results are very rough result, this one, because the mesh size is very big, and as you can see from the previous video, the size of the mesh actually are very important. And actually we have a problem here. As you can see on the right side, there are some water splashing and coming up, but on the left there is no water displaced. which means the conservation of mass is violated. This is because of improper material definition of the water. The material properties in the equation of state can be improved. So I rectified this mistake and shared the corrected file in the description. Alright, that's all for this sloshing tutorial. Thank you very much for watching. Don't forget to like and subscribe, and see you next time. Bye bye.